In this series of videos, we're going to be looking at the mock midterm for the summer 822 exam. This mock exam will be similar. We'll be reviewing the exam questions from last summer's exam, first midterm exam, that do not cover linear transformations. So this exam took place a little bit later in the semester, a week later, which means that they covered uh, things that we don't cover. Specifically, they looked over um, linear transformation properties that we aren't going to cover on our exam. So to find the term linear transformation, here, what I would think about is instead of term linear transformation, we can define other things like linear combination. Let S be a vector space or a subset of a vector space. V, then a linear combination of S is the sum of I equaling 1 to n of AI VI, where AI is in F and VI is in S. Note here for our linear combination, we don't need to contain every vector from S. It's just a sum of scalars times vectors from. Now, in the next question here, we're asking, is this vector 1, 2, 1 in the span? And this here, while it could be a long and involved questions where we set up a system of equations to determine it, this is meant to be quick. So what we're doing is we're checking, is there an obvious reason for why it's not in the span or an obvious reason for why it is in the span? And here I'm looking at it and I'm going, okay, I have 1, 1, 1. That's one of my vectors, and I want to make 1, 1, 2. Whoa! Or 1, 2, 1. If I just add this vector, 0, 1, 0, this equals 1, 2, 1. Put a 1 out front of both. That's a linear combination. So that vector is in the span. For these part A questions, to know what it means to be in the span, you say, okay, it's going to equal a linear combination, and there should be an obvious linear combination it equals, or an obvious reason why it cannot equal a linear combination. So here the answer is yes. Okay. Next, construct a linear system that can be used to determine if the following set is independent. I am looking at a linear combination of these vectors equaling the zero vector, so ax1 x plus 1 plus b 2x squared minus 1 plus c minus 3x squared plus 4x equals 0x squared plus 0x plus 0. And now what I'm doing is by expanding this, I construct a linear system, and I want to see what possible scalars there are. Well, this here equals 0 if and only if 2b minus 3c x squared plus a plus 4c x plus a plus minus b, so plus a minus b, this equals 0x squared plus 0x plus 0 if and only if a, b, c is a solution to 2b minus c equals 0, a plus 4c equals 0, and a minus b equals 0. We're collecting these common coefficients and matching them. The coefficient in front of x squared has to match, the coefficient in front of x has to match, and the coefficient multiplied by the constant has to match. Okay. Now, this is the if and only if relationship, but we are simply looking for this matrix. Have you constructed this matrix appropriately? In A4, we look at doing our complex multiplication or division, and here it's division. Now, with division, 3, or if I have 4 plus 3i divided by 3 minus 7i, to do this division, I multiply by the complex conjugate of the denominator, top and bottom. Now I'm going to expand the top. So 4 times 3 is 12. 4 times 7i is plus 28i. And then 3 times 3i is plus 9i. And 3i times 7i is minus 27. Divided by, and on the denominator, I have 3 times 3, or 3 squared, which is 9, plus 7 squared, which is 49. Okay. Well, here, 12 minus 27 is going to be minus 15. And 28 plus 9 is going to be plus 37i, divided by 9 plus 39 is 58. So I get 15 minus or plus 37 at I over 58, which I want to express this as a complex number. So it's going to be 15 over 58 plus 37 over 58i. And then the real portion is this value here. So it's going to be minus 15 over 58. And just for completion, if I look at the imaginary part of z, this is the real number multiplied by I. So it would be 37 over 58. Now this is assuming I haven't done any computation error. There might be a computation error at some point, but this is the general process. In A5, let V be a vector space. What is the only subset of V that is both a singleton, contains one element, and linearly independent? So here, what I want is I want the set V to have AV equals 0. Because I need a linear combination of V equaling 0. And A does not equal 0. Well, if A does not equal 0 and AV equals 0, we have a cancellation of property. This V vector must equal the 0 vector. So I need to have a set that is a single space and linearly dependent. So it's the set containing the 0 vector. Okay. Provide an example of a set S, subset of P2, such that S is a spanning set for P2. S is a proper subset of P2, but S is not a basis. So not a basis, but a spanning set. This tells me it's not linearly independent. So what I'm going to do is I'm going to start by taking a spanning set of P squared that is a P2 of R that is a basis. And I'm just going to add a vector. Now this here is a spanning set, but it's larger than the basis, which means it's not linearly independent. So that is how I'm going to construct this. Now, suppose I wanted to create a linearly independent set that's not a spanning set. What I could do is I could take a basis and remove a vector. Why are inconsistency systems of equations always non-homogeneous? This is because homogeneous systems always have the trivial solution or zero solution. So if we here inconsistent has no solution, homogeneous has the trivial, which means it does have a solution. So I have a solution. Thus are consistent. A. Consider an ordered set of three vectors in R2, such that the first two vectors in the orders are redundant, but the third vector is not redundant. So what this means to be redundant is that I want a set V1, V2, V3, such that V1 is in the span of V2, V3, V2 is in the span of V1, V3, and V3 is not in the span of V1, V2. This might sound challenging, but what I'm going to do is I'm going to let V2 equal K V1. So this is a multiple of V1 where K does not equal 1. Okay. If I do this and I make sure that V3 does not equal K bar V1, which is another linear combination of V1, then I have this redundancy. Because V1 equals 1 over K V2 plus 0 V3. V2 equals K V1 plus V3. But V3 does not equal A V1 plus B V2. And now I just have to pick V1s, what my V1 is. So I'm going to consider the set E1, 2, 0. And now not those, 0, 1. Or E2. So my set is going to be 1, 0, 2, 0, 0, 1. But again, this is me just picking random vectors. The big thing that I did is I said I want V1 and V2 to be multiples of each other. That way they're redundant, but that third vector is not redundant. A9, if S is non-empty subset of V, but S is not a subspace, what must be true about S? So it's a non-empty subset, but it is not a subspace. There's a bunch of things that could be true about S, but there's something that must be true. Okay, so if I'm not a subspace, then and I'm non-empty, then there exists a C in F and X, Y in S, such that Cx plus Y is not in S. And here what we're doing is we're negating the statement of the closure by the characteristic of closure statement. And we're saying if I'm not a subspace, then there exists this combination such that that it's not in S. And that to me is the most obvious statement to provide because the characteristic enclosure says that if this is always true, it is a subspace. So if it's not a subspace, at some point, this combination must not be true. And our final part A example is this a 10, which is looking at providing a counterexample. If I let T map R to R, provide a counterexample to show that if T of 0 equals 0, then T may still not be a linear transformation. You do not need to prove that it is not a linear transformation. What we're looking at is we're looking at functions that go through the origin that aren't linear. So we've got sine of x. That's one example. We've got e to the x minus 1. We've got x squared, x cubed, etc. All of those are valid functions. They go through the origin, but they are not linear functions.